So thanks a lot. So my name is Melanie Kaasinen. I'm a fellow at ESO, and my talk actually follows on quite nicely from Giovanni's introduction yesterday. So he was mentioning following up high redshift galaxy candidates with ALMA. So I'll present some of the lessons that we learned from trying that for one source. So this paper, or the associated paper, was actually published on ANA a few weeks ago. It's called To See or Not to See a Redshift 13 Galaxy. That is the question. And that question turned out to be pretty difficult to answer, actually. So a lot of the work I want to point out was done by Joshua van Marwijk, who's also attending MAYA, and he's giving a talk on other cool science that he does on Friday. So please also ask him about it. Okay, so our HD1 story started in December 2021, when this paper came out on the archive by the Harakane and collaborators. So they were looking for high redshift candidates between 12 and 16, using the Lyman break technique. So in case you're not familiar with this, I'll just go through it again briefly. So here you can see photometry on this candidate, HD1. You can see the spectral energy distribution here, 3 detections, and then a bunch of upper limits at shorter wavelengths. And this blue line here indicates a fit, assuming that there's a Lyman break, that is that the flux bluewoods of Lyman alpha is absorbed by a neutral intergalactic medium. And so that fit, in this case, implies that this is quite a high redshift candidate. Now, there are also other breaks in galaxy spectra. So this fit here, this redshift 3.9 fit, corresponds to a more quiescent galaxy, where this break is caused by a Balmer and 4,000 angstrom break. So Balmer break means that you have a lot of A-type stars, and 4,000 angstrom break typically denotes that there's a lot of metal absorption in the atmospheres of older stars. So this means that there's some degeneracy here, but seems to be that the fit prefers the higher redshift scenario. So this was pre-JWST. Of course, in the meantime, since July last year, there have been a bunch more candidates. So I'm just going to flash a few of them, some from the GLASS program here. You can see here the lower redshift potential Balmer break fit isn't even considered, although there's a tiny bump here. This, again, from GLASS. In fact, this candidate was also in the previous paper. Some work from the lensing cluster, SMAX, read the telephone number, but here's a redshift 12 candidate and a redshift 16 plus candidate. And some more from the Hubble Ultra Deep Field. Here you can actually see really nicely the difference between Lyman break spectrum and the fit Balmer and 4,000 angstrom break. And another one, and I'm not going to bore you with all of the rest, but I think I've made the point that there's a lot of candidates out there. And as of a few months ago, this was basically the picture that we had. So the highest redshift confirmation up until this year was GNZ11, so that was confirmed with HST. And there are these 2 candidates from the Harakane paper that I just showed, plus a bunch of JWST selected sources. Okay, but these are only candidates, so how do we spectroscopically confirm them? Well, at the beginning of last year, we thought that we could do this with ALMA. So to show you this, I'm just going to use this model spectral energy distribution of a star-forming galaxy. Here you can see where Lyman alpha emission would be, except at really high redshift. Obviously, this is absorbed, so you get a break. And here you can see true transitions that are covered nicely by ALMA, so the 0388 micron transition, and C2 158 micron. And we've heard a lot about those already in MAYA. Okay, so these transitions are covered at redshift 9, redshift 13, redshift 16, really up to the highest epochs with ALMA. So the idea was that we could actually use ALMA as a redshift engine. And ALMA has been used before to spectroscopically confirm galaxies using O3 and C2 emission. So here I'm showing some results confirming redshift 8 to 9 galaxies. Really bright, booming O3 line here. Also in this source, O3 and C2 emission. So there was some proof of concept at slightly lower redshifts. Okay, so Harakane in their paper that came out in December 2021 actually had some ALMA observations with band 6 targeting the O3 transition. So here you can see the spectrum extracted at the source position. Here you can see a zoom in tentative feature here. And collapsed over the spectral region, here you can see a moment 0 map. The red contours are the tentative 3.8 sigma O3 feature that they published. So with 3.8 sigma, you can't really confirm if a galaxy is at redshift 13.3. So what we decided was to try to confirm it by targeting C2 emission instead in band 4. Okay, so we proposed for DDT observations, and here they are. So again, here I'm showing now a spectrum targeting to C2 emission. This is extracted again at the source position, 2 different apertures. And you can see that where we would expect C2, based on that tentative O3 line, we don't see anything. And also, if you look at these moment zero maps, we don't detect anything there. But at a slight spectral offset of 190 kilometers a second and spatial offset about 6 kiloparsec, we find a 4 sigma feature. So we have another tentative line about 4 sigma, which is both spatially and spectrally offset. So we could have stopped here and said, well, we have another tentative feature. It's a redshift 13.3 galaxy, well, hey, but we didn't really trust the data yet. So we went back and took a look at the band 6 data that Harakane published as well. So here again is the same data. We extracted the spectrum. So extracted it from 0.5 arcsecond, which is around about the beam size. Can't see anything in the spectrum. See maybe a bit more for 1 arcsecond. And here you can see the moment zero map that we made. So again, you recover the same 3.8 sigma feature, but the spectrum's far from convincing. Now, if we make moment maps with different central velocities and different widths, you can see that this line disappears. So if we just slightly decrease the line width, there is no feature. Or if we shift it slightly, there's not really much there, but then you get a new line here. So essentially this tentative 3.8 sigma feature is really sensitive to the line width and the aperture size. Okay, so this means that we're now in the realm of noise statistics. So please brace yourselves because the next few slides are a little bit dry. So the first thing we did was look at the properties of the actual data that we had. So what I'm showing you here is a cumulative distribution function of the pixel values, the real data. And this is for different moment maps generated over different integration widths and different central frequencies. And these pixel values are normalized to the tentative detection. So in this case, to the tentative C2 feature and the tentative O3 feature. So what you should see is that there are loads of pixel values for these moment maps that exceed that normalized value, which means there are many things that are of greater significance than the tentative lines. And the noise properties are pretty Gaussian, so there's nothing strange happening in this cube. Okay, now the next thing that we did was to actually test these noise properties further by creating pure noise cubes. And I'm going to show these a little bit more in the next set of slides. So to make these, we used a jackknifing routine. So that is, we randomly inverted the sign of the data in the UV space and then re-imaged. So here now you can see the same plots, but in the middle and right panels for different noise cubes. And again, you can see that for pure noise, there are many pixel values that exceed the tentative features. Okay, so this doesn't look good already for the C2, the tentative C2 and O3 line. There's another way to look at this though. So there's a couple of algorithms out there that are used to find lines or find clumps. So we employed 2 of them, and I'll skip over these details, but you can ask me about that later if you want. So essentially we ran these algorithms to find clumps over a particular signal to noise threshold, that being mainly the signal to noise of the tentative features. Okay, so from that we have a number of clumps above some signal to noise, both negative and positive. And one way to see how likely these are to be real is via what's known as the fidelity. So this is 1 minus the number of negative clumps over certain signal to noise over the number of positive clumps. So if you have pure noise, you have the same number of negative and positive clumps above that signal to noise. So this value is 0. If you have many real positive line features, then this value tends to 1. Okay, so let's take a look at the fidelity as a function of signal to noise on the left for the band 6 data. So you can see here this dotted line is the signal to noise of the potential O3 feature. The fidelity is extremely low, it's practically 0, which isn't great for this line. You can also see there's a lot of both positive and negative clumps at that signal to noise. So this fidelity only approaches a value at which we would consider a line to be real at a signal to noise of about 5.2. So beyond that, we would be much more happy to call this real line emission. And really the same is true for the band 4 data. Okay, but we have some prior information about where the source actually is. So we can repeat this within some volume around the source. So assuming that anything within 10 kiloparsec would be associated with the same galaxy. So I'm just going to show that we did this for the mock noise cubes. So again, no source emission in there. And the upshot of that is basically that on its own, the C2 line is 50% consistent with being noise. If you just look within 10 kiloparsec, and the O3 line is fully consistent with being noise. Every single mock noise data cube had more than one positive and negative feature above 3.8 sigma. Okay, but we do have two data cubes and we have two tentative features, and they're within velocity difference that we might consider real, so surely that makes it more likely. So to test how likely we are to just get two noise peaks that are spatially and spectrally correlated, we found the number of matched peaks within 1,000 kilometers a second and 10 kiloparsec. So what I'm showing you here now is the number of matched peaks above a certain signal to noise within these constraints. So what I'm circling here, this blue data point, is the one pair of matched features in the real cubes. So positive matched features, i.e. the tentative C2 and O3 line. Now this blue line here shows you the results of matching different pairs of noise cubes and looking at matching positive peaks. So there's a mean of 0.5 greater than 3.8 sigma features in the noise cubes. But you can see that there are many matched pairs that have more than one pair of lines that actually aren't lines above 3.8 sigma. And this only drops to 0 beyond a signal to noise of 4.4. So anything less than that, you can get pure noise peaks that are matched or correlated both spectrally and spatially. Okay, so we basically conclude from that we don't have any convincing evidence of C2 and O3 line emission. So the likelihood of picking up two such features, neither of which are real, is at least 50%.
3 minutes, Melanie.
But maybe now that we have line upper limits and some more upper limits on continuum, we can revisit the redshift solutions, both using SED fitting and these line upper limits. So we did that, and it doesn't look good. We actually now have 3 potential redshift solutions. So one that we couldn't rule out is there's a low redshift dwarf galaxy scenario with a really high optical extinction. I haven't found such a thing in the literature, but nothing that we have data-wise can rule it out. It could also still be a passive galaxy around redshift 4. So although the ALMA observations would have covered other CO transitions, these should be way too faint for such a low star formation rate galaxy to be detected at our sensitivity. And we can't rule out the redshift 13 scenario, even though we don't detect the lines. So it could be that the ISM just has too low a metallicity or too low an ionization parameter or too high a gas density. And this is also shown in recent work by Masako Andel using simulations. So here you can see the O3 star formation rate ratio. This is where HD1 is, and anything below that is plausible. So could just be that the ionization parameter is very low. Could also be that it's at even higher redshift, in which case O3 and C2 just wouldn't have been covered by the ALMA observations. So really, these line upper limits have given us no more constraining power. So the takeaway for HD1 is that we can't rule out that it's at redshift 13, but the current data definitely don't confirm that. So if we want to find out where and exactly what type of galaxy this is, we probably need much deeper spectroscopy. This could be extremely expensive with ALMA. So it's much more likely that this will be done soon, and that there is actually a program on this with JWST NearSpec. So here I'm showing some examples recently of high redshift galaxies that were confirmed using NearSpec. So in this case, can actually resolve the Lyman break, which is quite sharp. So the lessons that I want everyone to take away, including me, is all too willing in the high redshift community where we trust a 3 to 4 sigma peak at the position where we expect to find it. Without testing how likely that is to be noise, we might well be quite wrong. And ALMA at these redshifts is not a redshift machine. So with only 1 to 2 hours on source, which is what has been spent so far on these high redshift candidates, there are no convincing detections. And I just want to flash that we're working on a tool for this. So Joshua is leading this project and is developing code that will allow the community to actually put a probability on these tentative features being real. And we're testing this on other JWST candidates, which already have ALMA observations. So here's just a table of some of their properties. Okay, I'll leave it on the lessons and I'm happy to take questions.